This is the Earth Science Classroom. Welcome back to the channel. This video is on a mixture of atmospheric science, physics, environmental science, and we're looking at the greenhouse effect and from a scientific perspective. Now, this is a well-known phrase that most people have heard of or know about. In this video, we're going to take a deeper dive into why we need this greenhouse effect, what causes the greenhouse effect, what air molecules are involved in the greenhouse effect, and why is it so important to understand this delicate balance of maintained heat on our planet. This is the Earth Science Classroom. Earth's atmosphere is a mass of air particles, air molecules held in place by the Earth's gravity, which is caused or formed by the size or mass of the Earth. So the Earth itself holds these lighter air molecules in place around the outside of our planet, forming a gaseous layer which is on average around 100 kilometers to 60 miles thick, which gets to what's called the Kármán line, which NASA deems as the start of space. So from the surface of the Earth up to around this Kármán line would be the majority of our atmosphere. Now, it's broken into four main layers. By the surface is troposphere, the next layer up is stratosphere, middle layer is mesosphere, and the fourth layer is the thermosphere. Now, the thermosphere stands for heat, kind of an oxymoron or a paradox because it is cold up there. However, it does have superheated air molecules individually, and it does include the ionosphere, which causes the aurora borealis and aurora australis in the southern hemisphere, the exosphere, which extends out really far into space, and the magnetosphere, which is the charged particles, which protects our planet from the deadly energy and radiation from the sun. So, as this diagram is not to scale, the troposphere is the focus of our video for the greenhouse effect, even though we can also discuss the ozone layer, which is a layer of 3 oxygen molecules chemically bonded in the stratosphere between 20 kilometers up to around 45 to 50 kilometers, and that is going to block out and absorb a lot of the ultraviolet radiation that we receive from the incoming shortwave radiation from the sun. Now, the majority of our atmosphere is contained in the two first layers, the troposphere and the stratosphere, that being 99% of the mass of our air molecules or the atmosphere. So the mesosphere, thermosphere, and up into the other three higher up, they constitute 1% of the air molecules because gravity pulls down the air molecules towards the surface of the Earth, which means that the stratosphere and troposphere have pretty much all of the air molecules. Now, the troposphere itself has 75% of all the air mass, and the stratosphere around 24%. And our focus for this video is the troposphere, the lowest layer which contains the majority of the air molecules in which this greenhouse effect is created or formed or established. And this layer extends up to around 15 kilometers up into the atmosphere or up to 25 around the equator. And that is what's called the tropopause, which is the boundary between the troposphere and the next layer, the stratosphere. Our atmosphere is a bunch of air molecules held in place around our planet in a gaseous layer by gravity. And in that atmosphere, there are certain gases that are more common than others. The two main gases make up 99% of the air molecules in our atmosphere. And again, this is concentrated in the troposphere and some in the stratosphere. So the biggest gas, the most abundant gas in our atmosphere is nitrogen, which is 78.1%, which is N2. Next is oxygen, O2, at 20.9%. So when you breathe in and respire, you breathe in 78% nitrogen and 20% oxygen. Now, again, those two add up to 99%. The rest is mostly argon, which is an inert gas of 0.9%, and the rest are all trace gases and very small amounts of different gases. The first one being the most common, CO2, carbon dioxide, at 0.04%, and we've also added in water vapor, which is the gas phase of water, with a range of 0.1 up to 4% of the atmospheric composition. So the 4% would be over a extremely humid tropical rainforest perhaps, on extreme cases, and the 0.1% would be over an extremely dry and arid desert condition, perhaps a cold polar desert or a hot desert like the Sahara or the Atacama Desert, for example. Our atmosphere is mostly composed of nitrogen and oxygen with a small amount of argon, and then we discussed the amount of CO2, very popular, well-known atmospheric gas, carbon dioxide, at 0.04%, and you also have water vapor with a range of 0.1 up to 4%. However, there are other gases that are present in our atmosphere which are important to discuss. They're called trace gases. They're called these because they occupy or have a very extremely small amount of each gas in our atmosphere, but they do play an important role, as you'll find out from this video with the greenhouse effect. So you have neon, helium, krypton, and hydrogen, which are in the atmosphere, but in very, very small amounts. Now, a lot of scientists and journals use parts per million and parts per billion to express the size or the amount of these gases in the atmosphere. I prefer to have decimals. Now, you have a lot of zeros after the decimal point, but it shows you how small of an amount these gases actually occupy in our atmosphere. And if we change the percentage, it can have a very large effect on our atmosphere. For example, methane, CH4, has 0.000019% of the atmosphere, and nitrous oxide, N2O, has 0.00000033%. To understand the greenhouse effect, we have to appreciate our atmosphere, its four layers, its composition, what gases are involved, and the energy that is being trapped or kept in our planetary system. So the energy, the source, comes from the sun, and this derives from the sun's core, the internal layers of the sun, and then is transferred through the sun's surface, through the corona, the sun's atmosphere, and travels at the speed of light across space in a vacuum. And this radiation is received by Earth after around 8 minutes and 14 seconds, and we receive this energy. It was called a solar constant. Now, parts of that energy, or a certain amount of that energy, is reflected back into space, either from the air molecules itself when it first hits the atmosphere, or from the clouds, or from the terrestrial surface, or the ocean surface, or even like snow. It's going to reflect a certain amount of energy back into space, and this is called albedo. And Earth reflects 0.3 or 30% of that energy we receive from the sun. So therefore, the Earth and its energy budget receives about 70% of the sun's incoming radiation. That radiation contains all types of different wavelengths, from short wave to long wave, and this spectrum, this electromagnetic spectrum of radiation, is received, and we take about 70% of that and use it for our planet. So we established how the Earth receives energy from the sun. There's a solar constant. There is a portion that is reflected back out called albedo. Now, what we do with that energy in the Earth's energy budget is important to understand, and how the gases in the atmosphere actually absorb this radiation. Now, it could be shortwave radiation, which is stronger, more powerful, coming from the sun, or it could be long wave energy, which has a longer wavelength and is less powerful, and that is going to be generally reflected off from the Earth into the atmosphere. Now, the air molecules and the different gases in the atmosphere, they have a different characteristic for their physics and chemistry in terms of the chemical bonding and in terms of their ways to absorb radiation. Now, the two ways is rotational states and vibrational states. So how the molecule actually rotates around with its chemical bonding with the elements and atoms, and how it vibrates, can match the resonance or the characteristics of the energy in order to absorb it. It's like having the right key for the right lock, and the air molecules can vibrate both rotational and vibrational states, and that would match the key, which is the energy, for them to bond and absorb. And once that air molecule absorbs the energy, it's going to be more excited and move more, be more energetic, and give off more energy. In this case, thermal energy, which is heat. So the more energy it absorbs, the hotter the air molecule will be, and the more energy it will transmit or release into the atmosphere. So the importance of how these air molecules or these atoms or elements are going to absorb the energy is very critical in the greenhouse effect, and understanding how our atmosphere actually absorbs energy and gives off heat. The four main greenhouse gases discussed in this video are CO2, carbon dioxide, H2O, which is water vapor, CH4, which is methane, and N2O, which is nitrous oxide. Our first greenhouse gas to discuss is the most powerful, the most abundant, and this is water vapor, H2O. Now, water vapor is the gas phase of water, and it has the ability to increase the temperature of the air through humidity, through the accumulation of water vapor within the atmosphere, actually pushing out nitrogen and argon. The oxygen stays the same, but you add in more of this water vapor, and the absorption of energy increases the air's temperature, which is called the heat index. So you could see a weather forecast in the summer saying it's 104 degrees Fahrenheit with a heat index of 120, because when you add in the humidity, it naturally adds in more heat, more thermal energy, which is why it's important to discuss for the greenhouse effect, because this air molecule has an extremely effective way at absorbing infrared radiation through a very wide range of wavelengths in the infrared spectrum. Now, it does this through three vibrational nodes, or three ways in which the air molecule H2O can bend and stretch to match the resonance of the long wave energy, which means it can be absorbed into this water vapor and heat up and become more energized and produce more energy into the atmosphere and transmit more heat energy into the atmosphere. So water vapor is an extremely powerful and diverse air molecule in which absorbs energy and plays a vital role in the greenhouse effect. However, it isn't really discussed in the same light as CO2, because a lot of the water in the water cycle is through natural systems where humans aren't really adding too much water vapor or additional water vapor into the system through various means of evapotranspiration and, let's say, volcanic eruptions. Our next greenhouse gas is CO2, carbon dioxide. Now, this is part of the carbon cycle, and there are two main ways that this gas can arrive and stay in the atmosphere. Now, its residence time, or how long it stays on average, is between 4 to 5 years, and there are both natural and anthropogenic sources of CO2. So the natural sources come from volcanic outgassing, which is the ash cloud, wildfires, ocean spray, and organic respiration. The anthropogenic sources, or the human activity caused sources, include the extraction, use, and combustion of fossil fuels in the energy industry and the construction industry, transportation industry, and agriculture. So anything that has carbon in its chemical composition and is then released in the atmosphere through combustion, let's say, that would be an anthropogenic source of CO2. So as discussed, CO2 has a small trace gas amount in the atmosphere of 0.04%, and it has increased over the past 150 years. However, we're looking at is how it absorbs energy. It is transparent for shortwave energy. However, like with water vapor, it absorbs long wave radiation. Now, the areas or the wavelengths that CO2 can achieve resonance, which means it has 4 vibrational nodes and 4 ways to create resonance through the chemical bonding between the carbon and the 2 oxygens, and that allows it to absorb in 2, 3, 4, and over 12 microns of wavelength, which is long wave radiation, which is infrared, that achieves resonance to absorb the energy along those wavelengths. So CO2 is a very good absorber of long wave radiation. Not as good as water vapor, but the key is that CO2 absorbs energy and is emitted into the atmosphere in different ways than just natural sources. Our next greenhouse gas is methane, which is CH4, so it's part of the carbon cycle, and it can get into the atmosphere through both natural and anthropogenic sources, the natural being through wetlands, swamps, bogs, and marshes, through release of permafrost environments, ocean exchange with the atmosphere, different kind of animals, and wildfires, whereas the anthropogenic sources of methane into the atmosphere come from the combustion or the incomplete combustion of fossil fuels through transportation, exhaust gases, the decomposition of waste through landfills, and agricultural practices, and also human-caused wildfires. So methane is an alkane, which means it has a single carbon atom with a single bond, bonding with the hydrogen atoms, and it can also go through oxidation in the atmosphere, which is the addition of oxygen to form CO2 and water vapor, and natural gas contains around 85% methane. So why is this important? It is extremely strong absorber of energy, and it has the capacity to store and absorb a lot more energy than CO2. Now, this comes from its 9 vibrational nodes, which means there's 9 different ways for it to stretch and bend through the 5 atoms and the different chemical bonds, which has the potential to absorb basically a hell of a lot of energy. However, it is such a small amount of or percentage in the atmosphere that it doesn't really reach its potential. However, if there was more methane added in large quantities, then you'd see a lot more heat absorbed by this methane in the atmosphere. So the infrared wavelengths that methane absorbs is on the 3, 6, and 8 microns, and that's produces resonance with the longwave radiation, and that is when the energy can be absorbed and then heat released from this air molecule. Our last main greenhouse gas to discuss is N2O, or nitrous oxide. Now, part of the nitrogen cycle, this gas has potential to heat the atmosphere over 270 times more than CO2 could. Now, nitrous oxide goes into the atmosphere both through natural and anthropogenic sources, the natural being through soils and the release from oceans, from lightning strikes, and from wetlands, bogs, swamps, and marshes, just like methane and CH4. The anthropogenic would be combustion and incomplete combustion of fossil fuels, just like with methane and CO2, and industrial processes, and again, agriculture, again with animal feed and soils and release from animals such as cattle. Now, nitrous oxide has 3 vibrational nodes, but the key is it's a linear bonding molecule, which means that the 2 nitrogens and the oxygen are in a straight line. So the amount of vibration is increased, and this is where you get the potential for the absorption of a lot of energy. Now, this gas is a very small amount, again, just like methane in the atmosphere, and it absorbs certain wavelengths of long-wave infrared radiation, and the peaks are between 3 to 5 microns and 6 to 8 microns. Now, there are windows in between that where this gas does not absorb energy, but between 3 to 5 and 6 to 8 is where the resonance is achieved through the vibration and rotation of this linear air molecule, and you can absorb energy, and then the energy is released as heat back into the atmosphere. The phrase or term, the greenhouse effect, is not a new term. It's been around for about 2 centuries when scientists started to investigate the role of certain gases in the troposphere that would absorb this energy and then release it as heat. And this was acting like a greenhouse effect, like the gases were the actual glass which would trap the heat inside the area. In this case, our atmosphere. So the greenhouse effect is defined as a natural system of releasing gases that absorb and trap thermal energy, thus providing an atmospheric temperature that is conducive for life to survive on this planet. Which of course is in conjunction with the distance away from the sun, our orbit, and the solar behavior, the solar cycles that we experience on Earth. The first work on the greenhouse effect was done by Joseph Fourier, a mathematician and physicist whose work with experimenting with metals and how the heat flux and how the air cooled down and heated up from his experiments, formulating a heat equation. These experiments showed him that if there were no absorbing gases in the atmosphere, the Earth would be a lot colder, and he assumed it would be around the minus 18 degrees Celsius or 0 degrees Fahrenheit temperature, which would be extremely cold, and life would not exist as we know it. However, there must be something in the atmosphere that is going to retain, absorb this energy and give off heat that provides the Earth this constant average temperature of 15 degrees Celsius or 59 degrees Fahrenheit. So his thinking was there must be something in this atmosphere to cause the heating that we experience on Earth. So the investigation into the greenhouse effect and what happens in the atmosphere started with Fourier in 1827 discussing the fact that the atmosphere must be heated through some mechanism process because of the temperature differences he found in his experiments. Then came John Tyndall in 1859 looking at certain gases and their radiative properties, in particular water vapor, CO2, and ozone. And he concluded from his investigations that these are all opaque characteristics, which means that the energy going in to the gases is being interrupted, absorbed, and he saw the potential for absorbing energy in these three gases between the wavelengths of 4 microns up to 80 microns and observing what's called the natural greenhouse effect. Then fast forward into 1896, Arrhenius studied the role of carbonic acid, known as CO2, in the troposphere and looked at this gas for its absorbing capabilities, and with its small quantity predicted that if this quantity would increase, so if there's more CO2 in the atmosphere, then that could possibly create an increase in absorbing energy and therefore heat released into the atmosphere, which would cause an increase in global temperature of the atmosphere. So that was back in 1896. Then a few years later in the 20th century, in 1901, Ekholm was the first person to coin the phrase the greenhouse effect and use the similarities between a greenhouse and the glass trapping the gases, trapping the heat inside the greenhouse in order to grow the plants more effectively. He linked that as a similarity to the gases like CO2 in the atmosphere that would trap and absorb the energy and heat the atmosphere within the troposphere, acting as though it was glass in the greenhouse. So disrupting the natural equilibrium and the natural incoming and outgoing energy amounts. So discussing not just the natural greenhouse effect, but the greenhouse effect with humans involved. In this diagram, we have the troposphere, the stratosphere, we have the tropopause, which is that boundary, that temp difference between the troposphere and the stratosphere. We have the albedo shown at 0.3, and we have the shortwave radiation and the EM spectrum coming from the sun, and the Earth keeping 70% of that energy we receive from the sun. The shortwave radiation is absorbed by the Earth's surface, 51%. The rest is absorbed in the atmosphere, in the clouds, in the actual air molecules or water vapor. Most gases are transparent to this shortwave radiation. We have here the red arrows signifying the emission of long-wave radiation from the Earth's surface back into the atmosphere. And this is where we kind of start to build our greenhouse effect, because this energy is long wave. It's different from short wave based on the wavelength of that energy. So anything that is above 750 or 800 or larger than that will be deemed long wave radiation, and in the infrared spectra. Anything below 750 would be in the visible light spectrum, which is between 400 to around 750. So shortwave, high energy, is received by the Earth's surface, and longer wave, less powerful energy is emitted by the Earth's surface. And this is what we're looking at for the greenhouse effect. As the Earth emits this long wave radiation, it interacts and absorbed with the greenhouse gases of water vapor, carbon dioxide, nitrous oxide, and methane at the different resonance, the different wavelengths, different range of microns based on each air molecule and their characteristics absorbed, and the energy through heat is then released back into the atmosphere and back within the troposphere. So the energy is not being lost back into the upper layers of the atmosphere or space. It is being absorbed by these greenhouse gases and then re-emitted or pushed out as heat energy back into the troposphere, therefore heating the atmosphere. So the natural greenhouse effect would be that average 15 degrees Celsius, and an increase in the greenhouse gases would, in theory, increase the overall average temperature of the atmosphere beyond 15 degrees Celsius. In summary, the greenhouse effect and how these gases absorb long wave radiation and emit the energy back into the troposphere as heat allows the atmosphere to be around 15 degrees Celsius on average, which is 59 degrees Fahrenheit. However, without any of these greenhouse gases present in the atmosphere of any concentration, like CO2, nitrous oxide, methane, and water vapor, the atmosphere would have an ambient temperature of around negative 18 degrees Celsius or minus 18 degrees Celsius, which is 0 degrees Fahrenheit. And that temperature, it will be very difficult for ecosystems, biomes, food webs, even the water cycle, the carbon cycle, the nitrogen cycle, all these essential flow of nutrients and elements and molecules on this planet would cease to exist the same way. And with that, the natural greenhouse effect is essential for life on this planet and plays a vital role in maintaining our planet and the atmospheric temperature. This is the Earth Science Classroom. Thanks for watching the video. If you liked it, please subscribe, like, and share. And if you want more content and videos on Earth science, please check out my channel.